Hello everybody, my name is Dr Marija, and this summer I'm a perm student at the Drndić lab. I'll be taking you today through my research.
Solid-state nanopore technology applications span various fields including DNA and RNA sequencing, filtration, and protein sequencing. To create such devices, we need a 12 by 12 micron meter squared suspended silicon nitride window on silicon chips using micro and nanoscale fabrication techniques. From there, pores down to 150 nanometers in diameter are milled into silicon nitride windows with a xenon focused ion beam. These devices can then be used on their own or can be made into more complex nanopore devices by the addition of 2D materials. To make our nanopores, we start in a clean room. So, what is a clean room? A clean room is a temperature, pressure, and light-controlled environment that filters pollutants from the air. The clean room at Penn is a class 1000 clean room, meaning there is no more than 7 particles per cubic foot greater than or equal to 5 microns in size. This is important because in the clean room, researchers routinely make features much smaller than 5 microns. We start with our substrate, which in our case is a 4-inch silicon wafer. First, we measure the thickness of the silicon oxide and silicon nitride thin films on our wafer using the Filmetrics F40 profilometer. Once we have that data, we can make our way to the spin coater to begin the photolithography process. Photolithography is the process that defines and transfers a pattern onto a thin film layer on the wafer. The first step is to spin coat a layer of photoresist, which is a light-sensitive polymer, onto our wafer. Next, we bake the resist on our hot plate at 115 degrees Celsius for 60 seconds. Pro tip: place the tweezers on the hot plate and let them heat up for 30 seconds before you need to remove the wafer. This will make sure that the cold tweezers don't thermally shock the resist. Behind us is our next tool, the SUSE Microtech MA6 mask aligner. This is where we load our photomask, load our wafer, and select an appropriate recipe for the UV exposure. The wafer is exposed to ultraviolet light as prescribed by one of the many recipes in the clean room. This recipe is a trade secret, so I'll leave it to your imagination. Don't forget to develop the resist and rinse the wafer. Next, we travel to a different room in search of the Oxford 80+ reactive ion etch tool. The RIE removes the silicon oxide and silicon nitride that are not protected by a layer of resist. From here, we make our way back to the Drndić lab, where earlier we prepared a 40% potassium hydroxide solution to anisotropically etch the silicon layer. The potassium hydroxide etches the 100 crystal plane at an angle of 54.7 degrees relative to the 111 crystal plane. If done correctly, this makes an empty upside-down square-based pyramid in the silicon layer. Lastly, my lab mentor Pia Bhatia carries out an isotropic buffered oxide etch back in the Quattro nanofabrication facility, which removes the remaining silicon oxide. Once we have finished the wafer, we can break the wafer into 100 5mm chips, and each chip will become one nanopore device. Once fabricated, solid-state nanopore devices can be used for many different kinds of research, including ionic transport measurements, gas sensing and separation, and the relationship between nanopore density and electronic properties.